Must have fixed it.
Can you just go back? So I think the bug is Q1. It's the same all the way through. You have it here, and here is the same.
Yeah, that's because we were sitting here for a while, and then we started changing.
But the zeros would be different.
Here, Q1.
So for Q1, we'd have 2 zeros. Okay, never mind. My bad.
Yeah, Q1 can go to 0 Q1, or it can go to 0 Q1 Q1, or it can go over to Q2.
Yeah. Okay.
Everybody see how we can convert any? This is just writing down the rules of the NFA into a grammar. Proof by example. All right, so here's a much harder language. We're going to have the language of all strings of A's and B's, where the number of A's equals the number of B's. All right? And we could worry about what the parse tree looks like, but we don't care about what the parse tree looks like. We just care about which strings are generated and which strings aren't generated. We want our grammar to generate every string that's in this language and not generate any string that's not in the language. So we're going to just throw in grammar rules as long as they don't add unallowed strings. So it's kind of like the concept of closure is useful. Remember, integers are closed under a successor and under addition and under multiplication, but they're not closed under division. So if you wanted to make all integers, you could start with all positive integers at least. You can start with 0 and add the successor rule. So 0's in there, hence 1's in there, hence 2's in here, hence 3's in there, and they all get in there. Right? So that's what we're going to do, a similar thing here. Right? You know, adding these extra rules, don't add extra integers. All right, so let's go up to suppose I told you that alpha was in the language. All right, what does that mean? Alpha has the same number of zeros as ones. Then can you tell me another string? Can you build up from alpha to another string that has the same number of zeros and ones? Hmm? I don't know how to multiply strings. Oh, I thought you said multiplication. What are we gonna concatenate on? Right? Yeah, we can concatenate. Like if alpha has the same number of A's and B's, then A alpha B does, and B alpha A, and A B alpha, and all these have the same number of A's and B's. Oh, we'll do that later. All right? So what rule, tell me a grammar rule that'll generate these. Right? If S is supposed to generate these things, then S spews out an A and B, or spews out a B and an A. Right, everybody see these rules? So then we can ask, what strings does this grammar generate? Actually, it's a trick question because it doesn't generate any strings, because we had to stop somewhere. We had to do the plot. Right? So now if we have epsilon in there, then the rules will give us A and B and B and A, and it'll give us all of those guys, and it'll give us all of those guys, and you keep getting longer and longer strings. All right? Does that make sense? And you can see that if these things are in, then we apply the rules. They also have the same number of A's and B's. So we're going to do a quick little proof here that every string generated by these guys is in the language. Meaning every string generated by these rules has the same number of A's and B's. Right? And it's going to be proof by strong induction on the length of the string. Do you guys remember strong induction?
What's the difference between strong induction and just regular induction?
Regular induction, you assume I minus 1 in order to assume I. And strong induction, you assume everything smaller. So here, I'll get to it in a minute. So HI is going to be the statement that all strings of length I generated by this thing are in the language. And so H0 says, well, how many strings are of length 0? Well, there's only the empty string is of length 0. It's generated, and it's in the language. It has the same number of A's and B's. And then by way of strong induction, we're going to assume H0, H1, all the way up to HI minus 1 is true already. We're going to assume that, and now we're going to prove that HI is true. And how do, yeah?
Why do you have the epsilon?
It's our base case. It's how we start off.
I thought you used it to plot.
Yeah. So if you're generating things, you'd be spewing out things, and then you stop. It's the base case.
So it doesn't move backwards.
Yes. So yes, we're kind of going backwards of what are the things that can be generated. Oops. Fuck. You didn't hear me say that. I didn't say that.
It's being recorded. We have proof.
Oh, I mean, it is being recorded, isn't it? Yeah, exactly. I'm going to go talk to the dean. All right. All right, so now, suppose beta can be generated by these things and has length I. If it can be generated, one of these rules was used last, right? So which was the last rule to be used? Beta has to be of one of these forms. And where alpha is also generated. But strong induction tells us if alpha is generated and is shorter, then alpha must have be in the language. Alpha must have the same number of A's and B's, right? And hence, beta has one more A and one more B than alpha. It's also in the language. Does that make sense? It's just a simple proof by strong induction. Hopefully people sort of followed it. People good with this?
How is the alpha shorter? Okay, it's one letter only, right? It's either A or B.
Well, alpha is 2 letters shorter than beta.
Well, it's logic. If beta alpha, that doesn't mean that if alpha beta.
If alpha is in this language, then beta is in the language. Again, actually, it's
Yeah,
assume it's an if and only if.
say beta is in the language, alpha is.
Our goal is the way we know alpha is shorter than beta, and the statement is that anything that's generated and is shorter is also in the language. All right, so the question is, do we get all strings? Are there strings here that aren't generated that have equal number of A's and B's? And I'm going to give you an example of something that's not. So here's a string, has the same number of A's and B's, but you can't have gotten it from one of these rules. You can't get it from this rule, right, because it doesn't end with an A and begin with an A and end with a B, or these ones, and it doesn't begin with an AB. So none of these rules will apply. So which rule do we want to use? We want to say suppose alpha and beta are both in the language. If alpha and beta are both in the language, then alpha beta is in the language. Right? And what rule do we use? S goes to SS. So you can split this in half and say this is the alpha and this is the beta. In fact, I kind of color coordinated it so you get that idea. Right? All right, so then we're going to see that we have a lot of rules here, but some of the rules are redundant. Do we need this rule? We can do this rule by splitting S goes to SS, and the first S gets the AB. So we don't need this rule. Yep?
SS generating an SS, right?
Yep.
So like, do we assume the S's are the same thing? Because since if it's the same, then shouldn't it be AABB and AABB or something? Or why is it like, a palindrome then, if we're generating the same SS?
It's not each S, this S is going to generate a string that has equal number of A's and B's, and so will this, but there's no link between them.
You can like generate any number, any way of
Any string of A's and B's that has the same number. Right, so we're going to get rid of those rules. And now these are our rules. And now we're going to prove that any string that has the same number of A's and B's can be generated by these rules. And the way we're going to do it is you give me a string with the same number of A's and B's, and I'm going to write a program which is going to give you a parse tree. Exactly. In fact, I shouldn't watch you so I'll yell them through. All right. So how do you do recursion? Remember recursion? I have an input that, and I can allocate work to my friends as long as what I give my friends is smaller and meets the precondition, right? And then my friend gives me an answer, and I use his answer to get the answer to my problem, right? So here's the program we're going to write. The precondition is I'm given a string that has the same number of A's and B's, and the postcondition is I output a parsing for it, a tree which says S goes to alpha, some trees, right? And how do I do it? Well, suppose, let's look at various cases. Suppose alpha begins with an A and ends with a B. Then it has the form A alpha prime B, right? So, no, it's just a different string. Alpha prime is a different string than alpha. So we recursively get a parse tree for the alpha prime, and then our parsing is going to be S goes to A, S, B, and then the parsing for alpha prime. People following this? All right, so it's a recursive program. I'm given an alpha. I'm given some string, right? And I want to know how to parse it. I want to build a parse tree for it. So I notice that my string begins with an alpha and begins with an A and ends with a B. So I ignore those and look at the string that's in between. Now the string that's in between, this alpha prime, it's a shorter string, right? And what can I give my friends? What can I recurse on? I can recurse on any string that's shorter that meets the precondition. And does it meet the precondition? Well, if my string alpha has the same number of A's and B's, and we remove one A and we remove one B, then alpha prime is going to also have the same number of A's and B's, right? So alpha prime meets the precondition. And so then we can recurse, and when we recurse, our friend, by magic, gives us, let me finish my little spiel here. My friend gives me my thing here, right? A parsing of alpha prime. Then what's my parsing going to be? S goes to ASB, and then S goes to alpha prime. And you see S is generating, this is how we have a parsing for alpha, because alpha, that's what alpha is. Yeah. What was your question?
So, like your program shrinks it to like substring.
Yeah.
Till you reach the empty string. If you reach the empty string, then it's possible.
Yeah, we haven't done the base cases yet, but yes. Yeah, exactly. It's a shorter string, yes, that we're going to give to our friend. People follow this recursive program?
Yeah.
Excellent. At least person does. All right, so similarly, if alpha is B, begins with a B and ends with an A, then we can use the same pattern. All right?
Professor, so what's the alpha prime here for? Difference between the alpha and the alpha.
So if I have some string, that begins with an A and alpha is my thing I want to parse. Right? So I'm going to say, hey, this here is my alpha prime. And what's my parsing going to be? My parsing is going to be S goes to A, B, alpha prime. Right? It's just another variable. So now we ask our friend to parse this. And how is our friend going to parse it? He's going to see it begins with an A and a B, so he's going to ask somebody to parse this. So this is going to go to S, which is going to go to A, B with this. And now it begins with a B and ends with a B, so he's going to split it in half. And he's going to go S, S, S. We haven't gotten that yet, but I know we're going to, right? And then this first part is going to go to A, S, B, epsilon, and the second part is going to go to A, S, B, epsilon. Everybody see how we got a parsing there, recursively? Hmm? A, B. This one goes to everybody good? Yeah. So that's how you get a parsing. So maybe I should make more slides, but I can't say I'm inspired right this minute. All right, so now let's look at the case. Everybody wants my picture all of a sudden. All right, so now what happens if it begins with an A and ends with an A? We're going to prove in a minute that if it begins with an A and ends with an A, then alpha can be broken into two pieces, a beta and a beta prime. Both parts have the same number of A's and the same number of B's. So then we can recursively parse the first part and recursively parse the second part, just like we did here. And then our parsing is S goes to SS, and the S, recursively, our friend gave us a parsing of S to beta, and our friend gave us a parsing from S to beta prime. Right? People buy that? Yeah. How do we get them? We took alpha. We're going to prove in a minute that if alpha has the same number of A's and B's, and it begins with an A and ends with an A, then it has to have a place that you can split it. We're going to prove that in a minute. Yes?
So alpha is anything beginning with an A, and beta prime is anything ending with an A.
No, not at all. Absolutely not. Beta, it's just, I'm claiming if it begins with an A and ends with an A, then you can split it. And in this case, beta will begin with an A and beta prime will end with an A, but that's nothing to do with what we're talking about here. All right, so similarly, if it begins with a B, ends with a B, then we're going to prove that you can do the same sort of split. And so we can do the same sort of code. So now, you're right, I don't have a slide for the base case. The base case is when it's the empty string, and then you just output the empty string. You're right, I don't have the base case. All right, so now what we're going to do, we're going to prove that if alpha is in the language, same number of A's and B's, and alpha begins with an A and ends in an A, then there's a place to split it so that the first part has the same number of A's and B's and the second part has the same number of A's and B's. So what we're going to do is we're going to have a function f of I be, when you look at the first I characters of alpha, what's the number of A's minus the number of B's? So you can see you get another A, you get another A, you get a B, you come down. You get an A, you go up. You get an A, you come up. You get B's, you come down. Right? And what do we know about this function? What do we know about F0? F0 is going to be 0 because we have no A's and we have no B's. Right? So we know that FA is 0. What do we know about F1? Has one A, so F1 is going to be 1. Right? People buy that? And then Fn, what do we know about Fn?
It's going to be 1.
Fn is going to have the same number of A's and B's, right? So it's going to be 0, right? Same number of A's and B's. So you subtract the number of A's from the number of B's, you're going to get 0. Now here's a little trickier one. What's Fn minus 1?
What?
No,
minus 1.
Minus 1, right? Because it ends with an A, so that A is going to be coming down, right? Right? What? Right? So now we know the function is up here is a 1, and down here is a minus 1, and at some point, and it's continuous, right? So the intermediate value theorem, if you've ever taken calculus, says that there's got to be a spot in the middle where it hits 0. And that spot is going to break our beta and our beta prime. Yeah.
How is that relevant to the n minus 1 equals negative 1? We know that it's going to be a 0.
Well, can you move your finger from here to here without crossing the line? No, that's the spot. The spot where you cross the line is the spot where this is going to be a beta because it's going to have the same number of A's and B's. And this is going to be beta prime. It's going to have the same number of A's and B's. Oh, we still have half an hour. All right. Therefore, we can conclude that this grammar generates everything that has the same number of A's and B's.
As far as I remember, the intermediate value theorem doesn't state that there's exactly one. There's more than one.
There could be more than one spot.
So you solve that like if there's more than one spot, how would you divide it?
Well, then you have a choice. You just have a choice of where do you want to divide it.